what I'm going to do over the next sort of 40 minutes approximately is give an update on the climate change science, the importance of understanding the science in terms of both emission reductions and in terms of the impacts of climate change. And what this first graphic is really showing is the increase in global average temperatures on the left-hand side. And we've already exceeded 1 degree of global warming since the pre-industrial period. And the, if you like, the update that I'm going to do is based on the 6th assessment report of the Intergovernmental Panel on Climate Change. And their reports came out towards the second half of 2021, and then 2 additional parts of the report came out in March and April of 2022, earlier this year. And it's clear that these reports are the most comprehensive assessments of both the science of climate change, the impacts of climate change in the, if you like, second working group, and then the approaches to reducing the magnitude of climate change, the mitigation assessment, which was the 3rd report. There will be a synthesis report that comes out later this year, but I'm going to try to synthesize the something like 3,000 pages of these assessment reports in 40 minutes, and picking out a few of the highlight graphs. I should point out that all of these reports, the full 3,000 pages plus all of the chapters, all the volume, are available online, and the references are included at the end of this presentation. And I'm also sharing this presentation as a PDF file after this talk, and Claire will be able to email it around to all the presenters. Claire, can we go to the next slide, please? Thanks. And as I've said, the IPCC report that when it was released in August of 2021, the science report, the Secretary General of the United Nations, Antonio Guterres, said this report was a code red for humanity. Somewhat earlier, and more from a, if you like, a business and industry perspective, he provided a really good summary of the science. The evidence is abundant. Global warming is indisputable. The planet will survive. And as we heard perhaps yesterday in the Minister for the Environment releasing the latest State of the Environment report for Australia, many species may not survive, and climate change and global warming are the greatest risk to natural ecosystems around the world. Yes, the State of the Environment report for Australia documents that very, very well, but the increases in extremes that have been experienced in Europe earlier this week also document that global warming is not just a long-term warming trend, it's a dramatic increase in extremes. And I'm going to focus on 2 different aspects when we look at the climate change risks, when we look at the Task Force on Climate-Related Financial Disclosures, which is really aimed at the business sector, but really the good way to think about climate change and climate risks is to break it up into the physical risks, the impacts of climate change and how they're affecting people, ecosystems, businesses, everything in, if you like, our northeast Victorian countryside, as well as how we can reduce the future magnitudes of climate change through a transition to a zero carbon economy. And that's much more than just transitioning to renewable energy through the electricity sector and stopping gas usage, as you've talked about already. I'm going to talk a little bit about how we can get to a zero carbon economy as well. Claire, the next slide, please. This slide is what I would argue is the most important one that I'm going to show you. And I won't do a poll now as to how many people have seen this graphic before, But for people who are skeptical about the human role in climate change, this is the answer to why human-caused emissions of greenhouse gases are critically important. And it shows in the sort of blacker curve that starts, and this graphic shows carbon dioxide concentrations over the last 1,000 years from data from ice cores in Antarctica. And the concentrations of carbon dioxide stayed around 280 parts per million until about 1800, and then they rose what is essentially an exponential increase. And we're currently racing through 400 parts per million. Now we're already at more than 410 parts per million of carbon dioxide in the atmosphere, and that's higher than at any time over the last million years. Now, we don't know from that set of observational data what was the cause. But there is a clear conclusion, and that's reliant upon the second, if you like, set of dots or graphs that's shown, which is almost like the mirror image of the other one. And this is the ratio of the atmospheric carbon dioxide concentration that's made up of the isotope carbon-13 in the carbon dioxide versus the more common isotope carbon-12 in the carbon dioxide. Carbon-13 is naturally occurring. Carbon-12 is naturally occurring. Carbon-12 is much more common, and carbon-13 is only formed by cosmic rays in the upper atmosphere. The concentration or the ratio of carbon-13 to carbon-12 stayed very stable and then plummeted from 1800 as a fraction of the carbon dioxide in the atmosphere. And that plummeting indicates that photosynthetically processed carbon dioxide, essentially what happens is that photosynthesis increases the carbon-12 carbon dioxide in the plant material relative to the carbon-13, because carbon-13 is a little heavier. Fossil fuels are made up of fossilized vegetation, plant material, and phytoplankton in the oceans. And they're compressed and they're fossilized. Or if there's land clearing, again, photosynthetically processed material is released into the atmosphere. So both land clearing and fossil fuel use, both coal and fossil gas use, increase the carbon-12 relative to the carbon-13 in the atmosphere. That's what we can see in this graphic. That's why this is so important. Essentially, 100% of the increase in carbon dioxide in the atmosphere over the last 200 years is due to human activity. Land clearing, burning coal, burning oil, and burning fossil gas. It's all due to human activity, despite what anyone else says. There is no uncertainty in this. And that is why we need to think about this as a long-term problem, because the natural systems that can take up carbon dioxide from the atmosphere and store it away would take more than 1,000 years to remove 90% of the carbon dioxide that we've added into the atmosphere in the last 200 years. So if we want to reduce carbon dioxide, we can't do it by just waiting 1,000 years and hope that nothing else happens. So the critically important problem is this is a long-term issue, and we need to stop further increases of carbon dioxide in the atmosphere due to burning fossil fuels and due to land clearing. And we have to maximize the uptake of carbon dioxide through planting trees, through storing more carbon dioxide in soils. If you like, that's the summary of why transitioning to renewable energy sources is critically important. So next slide, please, Claire. So now let's get back to the IPCC and its conclusions. And some of these graphics are going to be a little bit small, but the first one on the far left-hand side is the summary of the observed global temperature variations, the decade-to-decade variations. The black line on this is the observations from thermometers, weather gauges, observations across all the land masses and from ship observations. So we get a global average temperature. Prior to 1850, prior to the, if you like, observational period, we only have reconstructions from what are called proxy records, ice cores, tree rings, stalagmites and stalactites, lots of other different evidence. More uncertainty, you can see that uncertainty is showing essentially a decade-to-decade variations of the order of plus minus about 2 to 3/10 of a degree. Whereas the uncertainties in the observational records are much less than that. We want to look at the change from, say, the pre-industrial period, 1850, right up to the present. There's been a warming of about 1.1 degrees, with an uncertainty around that of plus minus about 1 to 2/10 of a degree. So yes, we've already had in the most recent decade warming of 1.1 degrees, and the Paris Agreement target, what all countries have agreed to, is trying to limit global warming to only 1.5 degrees. So what are the factors in terms of greenhouse gases and their contributions that have led to this warming of 1.1 degree over the last, essentially, 100 years, or since the pre-industrial period, 1850 to 1900? So that's what the next, if you like, bar graphs show. And the largest contributor to the warming is the carbon dioxide increase, which has contributed to roughly 7 to 8/10 of a degree of warming, from around 0.5 degree to 1.3 degrees or something like that. A substantial uncertainty. The next most important greenhouse gas is methane, about 0.5 degree of warming, and then nitrous oxide, about another 1/10 of a degree. And you add those all up, and you get sort of the 7/10 of a degree, and then another 0.5 degree from methane, and another few 0.1 degree contributions, and you end up with, we've got enough increases in greenhouse gases in the atmosphere over the last 100 years to have already caused 1.5 degrees of warming in the atmosphere. But we've only seen 1.1 degree. And that's because there are a couple of negative or cooling contributions from air pollutants in the atmosphere, from the aerosols associated with particulates, from nitrogen oxides, from essentially industrial pollution, and sulfur dioxides also from industrial pollution, which lead to haze. And that haze reflects sunlight, changes the, if you like, reflectivity in clouds, increases the cloud concentrations, cloud amounts, and cloud lifetimes, and they all lead to cooling of the climate system. So we've effectively had an offsetting contribution of around 0.5 degree of cooling, which is offset that 1.5 degrees of warming. If we rapidly reduce the use of fossil fuels in transport and in electricity generation, those sulfur particulates and nitrogen particulates will be removed, and the warming will accelerate. Now, that's a really good thing in terms of public health, but it will actually demonstrate that the warming we've got due to greenhouse gases could be and will get much greater, even if we don't increase greenhouse gases concentrations anymore. So this is part of what I would call the secret climate scientists business, which never gets talked about publicly very much. We need to rapidly stop not only emission growth, but rapidly remove some of the carbon dioxide and other greenhouse gases that's in the atmosphere already. Let's go to the next slide, Claire, please. Well, what about temperatures in Australia? Well, yes, we've seen across Australia rapid increases in temperature since around 1950. Temperatures on this scale, for which the baseline is 1961 to 1990, were about 0.5 degree below that baseline for the first 50 years of the 20th century. And now we're at +1 or +0.9 For the last decade, we're about 1.4 degrees relative to the 1910 to 1950 period. So in other words, Australia has warmed up substantially faster than the global average. And we have 1.4 degrees of warming in Australia. Since 1900 globally, it's only 1.1 degree. And look, that's not surprising. These are average temperatures over Australia, which is a landmass. Globally, it's the global land temperature and the global ocean temperature. Yes, we know that warming is faster on land, but the global averages that are talked about in terms of the Paris Agreement limiting global warming to 1.5 degrees, or where we're currently at 1.1 degrees, the land warming is about 50% greater than the global average, and that's why the Australian average temperatures is substantially greater than the global average. So when we talk about limiting, say, global warming to 2 degrees, or well below 2 degrees, only 1.5 degrees, the Paris Agreement targets, for Australia, the average warming will be much greater than those. For the global average of 1.1, we're already at 1.4 degrees. For 1.5 degrees of global average, we'll be closer to 2 degrees or more global average, sorry, Australian average. And for 2 degrees of global average, we'll be close to 3 degrees warming across Australia. It is the warming on land that is most relevant to the impacts in Australia, not the global average. Let's go to the next slide, please, Claire. Now, we know also that while climate change due to global warming is affecting global temperatures and temperature extremes, we also know that it's changing atmospheric circulation patterns and atmospheric rainfall patterns. And what we've seen in northeastern Victoria and in other southern parts of Australia, the southwest of Western Australia and the southeast, is significant decline in the cool season, April to October rainfall. And this map on the left-hand side of the screen shows the 20-year period, the most recent 20-year period from 2000 to 2019, as reported in the State of the Climate Report, relative to all the 20-year period rainfalls for the cool season, the 20-year averages. And the red colour is the lowest on record. And you can see that much of northeastern Victoria is the lowest on record in the most recent 20 years relative to 1900. Well, 1900 to 1919. So yes, there's been significant declines in rainfall in the southwest of Western Australia and in the southeast of Australia, but particularly in the northeast of Victoria. If we switch to the warm season, for much of Australia, the pattern is quite different, and that is that we've actually had increases in warm season, October to April rainfall, particularly in northern Australia and particularly in Western Australia. And one of the few parts that's seen an ongoing decline in rainfall in the warm season has been Victoria and Tasmania. And while the decline in rainfall hasn't been strong in the warm season in the northeast of Victoria, there hasn't been the same sort of increases that you get in, how would I say, Queensland and the far north of Northern Territory and the Western Australia. Let's go to the next slide, please, Claire. I'm going to use some of the graphics from the Victorian Climate Science Report that was released with a new set of climate change projections. And these ones focus on area average changes in frequency of climate extremes over the last 120 years, or since 1910 across Victoria. And the top left-hand graphic shows the number of unusually hot days averaged across Victoria and how they've increased from 1910. Now, an unusually hot day here is defined as days which are hotter than, if you like, what's called the 1 percentile, hotter than 99% of days in each year. Now, 1% of days in each year would on average be around 3 to 4 days above the hottest 1% of days. And we can see that from 1900 or 1910 to 1950, the number of days wobbles between 1 and about 5 or 6. Of course, 1939 was a very hot year across southern Australia, major bushfires. We can also see that from 1970s onwards, there's been very substantial increases in the typical numbers of very hot days, rising up to, in 2009, more than 15 days in 2009, which were above the 1 percentile. Whereas instead of getting around 3 to 4 days, it's above 15. And in fact, many years have had 5 to 10 days above the 1 percentile. A substantial increase in the very hot days. And at the same time, we see a major increase in the number of days with very high fire danger, particularly not just in summer, but in springtime. And the largest increase in fire danger has been in spring, with an extension of the very high fire danger days to be occurring much earlier in the season in springtime. And yes, there were major examples of that in the 2019-2020 period, with very dry conditions and extreme fire danger that very much affected the northeast of Victoria. Let's go to the next slide, please. I need to speed up a little bit because I know we started a few minutes late, but I've got a few things that I wanted to cover. Let's look now at what we can plan for into the future. And I don't encourage you to use a crystal ball to look into the future, but rather I encourage you to look and make use of climate model simulations and climate model projections to look at what we can expect for the climate in the future. And there are two different types of, if you like, climate data sets that are shown in here. They're climate model simulations in the colored bands that are run either as climate model simulations with the observed increases and future projected increases of greenhouse gases. That's the blue band, and then the orangey band or yellowy orange band that increase over time. And these are showing the observed decade to decade temperature variations from the climate model simulations, more than 20 different climate models. And superimposed, or maybe it's underneath that, there is also a set of climate model simulations, the same models, but now run without any increases in greenhouse gases over the last 120 years. These climate model simulations were actually started way back in 1850 in simulated time, not in the real world, but started in 1850 in simulated time. We can see that the grayer bands, which show the decade to decade temperatures in the climate models, are essentially horizontal. The jagged blue line is the year-to-year temperature variations in Australia, averaged as I showed before. 2019 was the hottest year. And the black line, the thicker black line, is the decade-to-decade observed temperature variations. That lies within the range of the model simulations without any increases in greenhouse gases from 1910 to 1950. And then after 1950, the observed increase in decade-to-decade temperature variations across Australia can only be simulated in the climate model simulations that include the increases in greenhouse gases due to human causes. In other words, we can only explain the recent warming due to the increase in greenhouse gases that I talked about already, due to human activity, burning fossil fuels and by land clearing. So what else? What about if we want to look at, say, those rainfall changes and what happens in the climate models? But before we change the side, I want to look at the extension from 2020 to 2040 in the climate model projections, which is shown in that coloured band. 2019 is the hottest single year across Australia in the observational record. But if we look horizontally, the projected temperatures for 2040 and beyond, 2019 would be a normal temperature year, not a record high. It would be an average year. And so the sorts of temperatures that were experienced in 2019 are likely to be an average year for the 2040s and beyond, with ongoing warming that's locked in due to the increases in greenhouse gases we've had already. Let's go to the next slide, please, Claire. In the same way that we've got locked in changes in temperatures, we've also got locked in changes in rainfall. And unfortunately, what this graphic shows with the black line, the Victorian average 20-year by 20-year rainfall averaged across Victoria. The year-to-year rainfall, as shown by the blue lines, is very, very large. But notice there's a blue triangle, and this is the projected rainfall change from the 1990s out to the 2030 period. And it's shown as a wedge because it starts off with a baseline from 1985 to 2005, centered on the 1990s. And then it's essentially running up to the projected rainfall in Victoria right out to the 2030s. The worst part is that the most recent rainfall changes from the 1990s to the 2010s, the most recent 20-year average rainfall, is tracking at the worst case of rainfall decline. This is not just wintertime, this is the annual average rainfall. In other words, unfortunately, the climate models, when we just take the mid-range estimate, are underestimating the observed changes. Let's go to the next slide, please. What about other projections? Well, look, I've talked about the Paris targets of 1.5 degrees and 2 degrees warming. This shows the range of climate model projections right out to 2100 for a range of different future emission scenarios for what are called socioeconomic pathways. And unfortunately, 2 degrees of global warming is pretty well locked in for all of these scenarios. And in a couple of slides, I'm going to show you scenarios for the future in terms of emissions, but very low emissions, rapid reductions in emissions are going to be required to limit global warming at the end of this century to below 2 degrees of warming, and only give a greater than 50% chance of doing that. In fact, a much smaller than 50% chance of exceeding global warming in the future. Potentially, and remember, these are global averages. For Australia, 2 degrees of global warming means 3 degrees of Australian average warming, and 5 degrees of warming, which is essentially the business as usual, no reductions in emissions, leads to 6-7 degrees of Australian warming. Best estimate, even with all the commitments we've made already, is 2 degrees of warming or more. Let's go on to the next slide, please. Claire, can we move on to the next slide? Thank you. Within the IPCC assessment in the climate change impacts, there's lots of discussion of impacts of climate change, and the high confidence key risks are reported in a 2-page regional fact sheet for Australia and New Zealand. And some of the highest, very, very high confidence impacts are due to increases in heat waves in the oceans that are having major impacts on coral reefs, particularly the Great Barrier Reef, and increases in heat-related mortality and increases in wildfires or bushfires associated with the heat waves. And look, we've seen plenty of that already in Victoria in 2009 and 2019, 2020. Unfortunately, Europe is experiencing that at present. I could go through the impacts in cities and settlements, in infrastructure due to many of these increases in extremes, like the floods we've seen in New South Wales and Queensland earlier this year, like the increases in severe storms, the increases in sea level rise leading to erosion in many of coastal areas, and the increases in bushfires. Those are leading to impacts on ecosystems, on cities, on infrastructure all around Australia. And unfortunately, the 2019-2020 bushfires and heat waves and the impacts of the smoke, as well as the flooding that we've experienced, have demonstrated this final conclusion I've listed here: the inability of institutions and governance systems to manage climate risks. Because every person who's been affected by these recent extremes would unanimously agree that the institutional systems for managing the climate risks and the governance systems have been inadequate. Let's go on to the next slide, please. I'm going to skip over this one, Claire, because I've already talked about it to some extent, but the bottom line conclusion from this slide is that we have had rapidly growing emissions from 1990 right up to 2019. And we're now at 50 billion tonnes of greenhouse gas emissions in 2019. There was a significant reduction in 2020 and in 2021, nearly 6%. And that's what the downward blip is. But that downward blip is tiny relative to what is needed to limit global warming to the 1.5 degree Paris Agreement target. We would need to have that 6% emission reduction every year for the next 20 years to limit global warming to well below 2 degrees, to down below 1.5 degrees. And then we've got to get to negative emissions of carbon dioxide from human activities. Not zero emissions, but negative emissions. Let's go to the next slide, please. Well, what's Australia been doing? Well, look, what's shown in this graphic is critically important in the different colours, and that is there are only 2 sectors for which there's been significant emission reductions. It's easier sometimes to see the numbers which are on the next graphic, Claire. So let's move to the next table on the next slide, please. If we look at where we were in 2005 and what the the last government's target, which was a 26 to 28% emission reductions, and the projections from 2019 to 2020, the only 2 sectors for which there's been significant emission reduction has been in electricity, due to renewable electricity, and it's hoped to reduce the emissions in the electricity sector to down to 50% by 2030. But that will require a doubling of the emission reductions in the electricity sector alone, from more solar panels, from more large-scale wind and more large-scale solar. And in practice, the new government is looking not at a target of 26 to 28%, but a target of 43% emission reductions for Australia by 2030. That requires emission reductions in all sectors. The only other sector that's shown significant emission reduction since 2005 has been land use change and forestry, but they were already at negative emissions in that sector because of the expansion of managed forestry. We've got to think about how we can reduce emissions by transport, by agriculture, by stationary energy, by waste and industrial processes. And unless what emission reductions are possible are achieved across all the sectors, It cannot be achieved through electricity reductions alone. But the electricity reductions then have to provide solar power and wind power electricity to support transport. And we have to convert to essentially rapid emission reductions in that sector. Let's move on, Claire. I'm now just going to focus on a couple of, if you like, summary slides on what we expect in terms of the physical impacts of climate change. We're expecting ongoing increases in very hot days and mean temperatures, increases in the intensity and frequency of the fire season, declines in alpine snowfall, which is why I'm going up later this winter up to the snow, impacts on coastal areas, reductions in cool season rainfall, and increases in more intense downpours, which means more erosion and more flooding. Not much good news here. There is some benefit for agriculture from the increase in carbon dioxide in the atmosphere that isn't sufficient to offset the adverse impacts from all these climate change related impacts. Let's go to the next slide, please. Oh, this is interesting. It didn't quite come out the way I thought it was going to. Unfortunately, the text had been black and now it's gone white as it's been shifted. I hope you can read the text. This is the projections from the Wodonga from the Victorian Climate Projections 2019 report for the Ovens-Murray region. Look, the projections for medium emissions are about 2 degrees of warming by 2015 in Wodonga for the maximum temperature, ongoing declines in rainfall. But what I wanted to focus on is the changes in the frequency of days over 35, as well as the changes in the frequency of frost days. Frost days are really important for stone fruit and for grapes. We're expecting to see declines in frost days and substantial, nearly doubling in the days above 35 Celsius. So we're going to see many increases in heat waves and reductions in the cool temperature needed for agriculture, as well as, unfortunately, increases in evapotranspiration, reductions in water availability from stream flow and in, for instance, reservoirs like the Hume Weir. Next slide, please. Look, there's a whole range, and I'm going to skip over this one and probably the next one as well, just so that we can allow some time for questions. It is clear that what is needed is adaptation to these major changes of climate that are still locked in. And let's go to the next slide. We also need to manage emission reductions and transition to a zero carbon economy as quickly as possible. And that means, as you've discussed in the earlier presentations, more efficient use of energy, more insulation, reductions in energy use, greater use of solar panels and wind power, zero carbon and low carbon energy uses. We've got to improve carbon sinks. We've got to ban deforestation. We've got to improve forest management. We've got to improve the uptake of carbon dioxide in soils. We've got to make better use of bioenergy with carbon capture and storage, and also think about lifestyle and behavioral changes. You don't need to replace your computer, your clothes, or your vehicles as frequently has been encouraged by the advertising programs. The best solution to climate change is to ban advertising. Oh, I should add, that's not going to happen because the advertising industry dominates the Australian economy. Last slide, Claire. The next one. Oh, no, you've skipped one. There should be one more. That's it. My key messages are that The human influence on the climate system is clear. The more we allow greenhouse gases to be emitted, the more will be global warming, and the more we have more severe and higher impact climate changes, more frequent extreme events. And the only clear solution is to reduce greenhouse gas emissions from burning fossil fuels and land clearing. Every ton of carbon dioxide emissions adds to global warming, which makes the climate change impacts worse. And unfortunately, even the current government is going to allow ongoing expansion of mining for coal for the foreseeable future. That's not a good solution, and that makes global warming worse. We know how to limit climate change. We know how to build a more prosperous and sustainable future. And this slide was not from this IPCC assessment. It was from the IPCC assessment that was released in 2013, now 9 years ago. It's a pity we didn't follow these recommendations 10 years ago. I'm going to hand over back to you, Claire. You can unshare your screen and we'll try to have some questions